Hi, I'm Moshe Acevedo. This is my presentation on the design and modeling of a radio direction finder. We'll be going over through some history of automatic radio direction finders, a system model to propose as my design for a radio direction finder, and a simulation for this model. Automatic radio direction finders started as use for vehicles. Aircrafts use it to find stationary beacons, finding airports, and the same applies to ships, which use it to navigate towards docks, wherever in the world they are, they can tune into a frequency and locate a specific beacon. This system is purely analog and consists of two loop antennas whose magnitude are taken and put through an amplifier. The received signal drives a DC motor which turns an indicator. And once this signal goes to zero, at the position where the loop is pointing perpendicular to the direction of the beacon, the indicator will be, of course, also perpendicular to that direction and point directly at the beacon where the port may be. This system also uses a sense antenna to get rid of some ambiguity in the direction and uses it as reference for the antenna, for the amplifier as well. Our system takes some inspiration from that, but rather than using a loop antenna, we use a more advanced directional antenna. The system that I imagine will ideally use any directional antenna, but the Yagi antenna is the perfect fit for this system. What I intend to have is a Yagi antenna mounted on the shaft of a motor with a sense antenna for reference. And all we need to do for the system is to take the difference of our reference signal to our received signal from our Yagi antenna after some normalization of the signal strengths. And as long as the difference is greater than 0, then we know that the motor has to rotate in order to point the antenna towards the direction. What we eventually get is behavior that leads the antenna around a circle until it points towards the signal source. The antenna radiation pattern is important to note for these experiments. Since the Yagi antenna and whatever directional antenna we imagine to use for this system has this general form where we have a peak at 0 where it's pointing directly at the source and a strength that's less than unity at every other point. We aim to have this behavior so that when we do our comparison, we know that the system will be, we know that the motor has to rotate, and we don't really care that there are lobes around the side, which should normally mess up the reference, but since our system will use discrete values, just indicated by whether the signal strength is less than or greater than the reference signal, what we use for a model is a much simpler function which takes that same pattern and has one point where the signal strength is 1 at 0 degrees, and then all around the circle has a signal strength that's less than 1. This is the model that we use for a Yagi antenna, and the signal strength that we extrapolate in our system model is based on this function. To continue on the modeling, the control system that we intend on using uses the motor as the plant. This transfer function that we have on top describes the angular velocity to voltage transfer function of a DC motor. All these parameters are dependent on the motor, and the motor that we used is an example motor provided by MATLAB in an example. The parameters are also adjusted to adjust for the wave of the antenna, and all of it is determined in MATLAB and using our system blocks. Lastly, our controller of choice is the PID controller. The PID controller has benefit that comes in its parts. It consists of a derivative portion, which helps with the transient response of the system, improving on the speed and response time of the system. It also consists of a proportional portion, which helps with the stability of the system and helps manage the overshoot of the system. And finally, an integral portion, which ensures that the input and output are one-to-one, essentially reducing our system error our steady state error to 0. For the parameters of this controller, rather than going through the intense calculation that would be necessary to find the parameters, since the calculation is very complicated, what we instead use is software to assist us in finding these parameters. The software of choice, of course, is MATLAB, where we use the PID tuner tool to find the parameters of our system given a desired response time. So we modeled our system in MATLAB and then proceeded to use the PID tuning tool to get the desired response. I decided that the response time for our system should be just fast, only so fast. The rise time of our system is about 0.1 seconds. Our overshoot is much less than 1%. And so long as our system responds this way, the system should work just fine. In our Simulink model, we start by initializing with some values. First, we define a threshold for our comparator. The threshold is really important for the function of the system. We have to make sure that our reference signal is greater than the expected noise on our frequency. If we receive too much noise, then the behavior of the system will be very irregular at the final position and may never find the direction of our signal. So it's really important that this is at least greater than the highest noise we expect in our system. We also start by initializing a position for our Yagi antenna, which is input into this Yagi signal strength calculating block, modeling the function that we saw before. Another input for this block is the position that we receive from the motor. And what we use for reference is a signal of 1. Of course, all our gains are all normalized, so the difference will always be some number between 0 and 1. When we take the difference of our signals for the function of our system, we run it through the comparator. The comparator gives an on or off signal for the motor. This signal drives the motor, which is in a feedback loop with this controller, and continues until the comparator gives an off signal. The comparator will give the off signal once the calculated signal strength of our Yagi antenna matches our source. So, in order to accurately model this, since the output of our controller will be a velocity, we integrate the output and use that position as input for our antenna. That way we can accurately model the antenna rotating and the relative signal strength that we receive when the antenna is at a specific position. For graphing purposes and for presentation purposes, I went ahead and selected the position of the motor to graph, the velocity of the motor to graph, and the compared signal strength to graph, as well as the error between our starting position, our current position, and the final necessary position to go towards our signal source. For the simulation, we assume that the signal comes from a 0 degree angle to make the calculation easier. Of course, if the system needed to be initialized in some other direction, we only need to change the starting positions and the extra positions otherwise. The results are as follows after a simulation. The blue line shows the position of the controller, the orange line shows the velocity of the controller, and the yellow line shows the difference in our signals. As we can see at the start of our system, the signal strength starts with a difference of 1, since we started our antenna completely opposite to our source. With that signal red, the motor turns on and stays on for a while. The position increases linearly until the difference of our signal reaches 0, where the motor stops and then the position stops at about pi, which reflects the necessary position that we needed to go from directly opposite to our signal. We show the difference in our error graph, which since our units are in radians, our signal needs to travel about 1 pi radians in order to get to our signal, and this shows that this decreases linearly until it gets to 0. Of course, it's not exactly at 0 since we're dealing with a real system, and we'll stop very, very close, but the precision may not be necessary for application in real life. As you can see, the system works and considering that the system only needs the control system and 2 antennas, it makes for a very, very low cost system compared to normal systems that are used for direction finding. And I hope to continue on this model, to expand on it a little bit, and build this in the near future.